Hey, Physics 30s. I just wanted to go over this uh, kind of harder graphical analysis question here. You can see this is a nice little graph, but it has some kind of weird axes to it. It's got like this tan theta, with no units, obviously. And, well, not obviously, but okay. And then it has current. It's very similar to the lab that we did. This case, they have this kind of wire here hanging between two wires. They have this conducting rod, hanging between two wires, and it's free to swing back and forth. So as they pass electricity through it, it gets forced one way because of Lorenz's law, using your hand rule there, your third hand rule. It'll push off one way, so it'll swing off, but it won't swing off completely because gravity is also pulling it down. So how do we do this, lab? Like, what is this? Like, exactly what are they doing with this graph that they created here? They've created this graph, this tan theta graph, as a function of current. You can see here, it's created this nice little straight line. You don't see any of their data points or anything, but this is just their line of best fit. So the question says, based on the line of best fit, what is the magnetic field strength that the current carrying conductor is within? Okay, it's very similar to the lab, but they just did it a little bit differently. So they didn't use a force downwards, they're using a force sideways here. They got this rod, it ends up being 2.5 grams, which is going to be nice and useful for later. And they got the length of the rod within the field here as about 8 centimeters or so. So it's 8 centimeters in there. Okay, so let's figure out what they're trying to do here. So why did they decide to use, let me see if I can get my pen here working. Why did they decide to use tan theta for this? Okay. Let's look at this diagram and figure out what's happening here. So first of all, I can see that if I were to draw in my magnetic field strength, or magnetic field here, it's going from north to south. So there's my magnetic field. I probably don't necessarily need to draw this part, but that's the direction my fingers are going to go. If I use my left hand here, I'm just going to go right to the screen to this. It'd be kind of confusing. Watch me do it. My fingers are going upwards. My palm, the reason my palm is going off to the right there is because that's the direction I got deflected. So my thumb here tells me which way, my thumb tells me which way the current is going through that wire, and I can see that based on my left hand rule, that this current is coming out of the page. Okay, so I don't know exactly. It looks like the current is flowing this way through this wire. So my field is going upwards here. And it's got deflected in towards it. Yeah, I can kind of see currents flowing through the wire there. That's not necessarily what we need to find. That's kind of just useful to know. But what I'm going to draw here instead are the forces acting on this rod. So the force based on my hand rule, my magnetic force is going inwards here. And gravity is holding it down. And tension is in this wire. Okay? So I have these three forces, and if it's just sitting there suspended, so it's suspending the rod, right? I'm going to assume that all of these forces, these three forces, must balance each other out. Okay, so hopefully I can figure out why they're using the tan theta because of that. Well, from the picture, you can see that this angle here, this angle up here is theta. You can see that's what they have here. So if I were to draw a triangle around my tension force and produce components, this angle in here is also theta. Okay, so now everything's got to balance out. So the two forces that are going side to side must balance out, and the two forces that are going up and down must balance out, or at least the components. So everything in the x and everything in the y must add up to 0. So we have gravity going down, okay? So gravity is going down, but that means this must also be equal to the vertical component of the tension. They must be equal to each other, okay? Because they have to cancel each other out. And then I could also say that the force that's pulling it sideways, sorry about that, it jumps around once in a while. What just happened there? Oh, that's better, okay. The force that's going sideways here must balance out the tension force that's horizontal, because they have to add up to 0 here. Sorry, this thing's just jumping all around the place here. Okay, so I know that much so far. So I'm just going to write this information down here within the question part here. We give us a lot of space here to do this question. Okay, so I know that the gravitational force downwards has to balance out with a tension force that is vertical, and the magnetic force sideways must balance out with a tension force that is horizontal. Okay, putting these absolute values in here because I'm not worried about direction, just worried about the magnitudes must be the same to make sure it adds up to 0. So what I know over here is I can calculate my force of gravity by going mass times gravity. I got the mass. Question says 2.5 grams. And this piece here, I'm going to worry about this part later on, but this here, if I wanted to calculate this, this is going to be Ft, and then based on the triangle that I have up here, this is the vertical piece. This is going to be cos theta because it's the adjacent side. So this is the side we're looking at here. That's adjacent to the angle, so that's going to be a cos theta. So I'm going to just change that to be cos theta. On this one over here, I have ILB because this is a current carrying wire. And over here, this would be Ft sine theta. Okay. So what I'm going to do is I'm just going to try to get rid of the Ft as much as possible. I want to relate the two sides together. So rather than thinking about this, I'm just going to think about that triangle. I'm going to label the triangle differently. So I'm going to say, here's my Ft that was going off this direction. This piece here that's going straight up, that's my gravity. That's Fg. Well, at least the same magnitude as my gravity. The piece that's going sideways is my Fm. Well, at least the magnitude of my Fm, to make sure that this balances out. So how do those two sides relate to each other? Well, I'm not going to bother with this. So you can put these two equations together, but what I'm going to do is I'm going to relate them with this angle instead, kind of ignoring the Ft. So these two, this is the opposite side. This is the adjacent side. So opposite adjacent, you can't see my trig ratios up there, but opposite adjacent is tan. Ah, there's a tan. So this is where that tan theta popped up from. Okay, so this is good. Tan is opposite, so that's Fm over Fg, and we already talked about the formulas for those two, ILB and Mg. So this is equal to tan theta. Now I can get the same thing by combining these two formulas together. So if I were to put those two together, I can isolate for Ft on one side and substitute on the other side. It would eventually change into this formula as well. So you could do that as well. So here I have a formula now that relates everything that I have. I have all this stuff in this formula as far as I know. What do we have? Let's go back up here. Oh, current is my manipulated variable. So that's my manipulated variable, which is my x variable. We have the length, which is 8 centimeters here. So we have this. We're looking for this. This is my control variable. We have the mass. We have gravity. Also, sorry, we also have my responding variable, which is my angle. So I have all this stuff here. Actually, all of this is my responding variable according to that graph. Okay, so there's a couple ways we could do this now because this is a nice linear line. We can relate this to y is equal to mx plus b, and it looks like relatively it's going to cross the origin, so the b is not there. So I can rearrange this equation, but I can also just rearrange it for how I would calculate my slope. It would be rise over run. So first of all, let's find some good points here to calculate my slope with. Actually, this point right at the very end is nice. And I'm looking for points that are pretty good distance apart from each other. This point right here looks pretty good. Okay, so I'm going to use those two lines to calculate my slope. So I'm going to draw a nice little triangle here. How do I do that? We're just going a bit slow today. Just going to draw a nice triangle going across. Right about there. It's a bit thin, isn't it? Make it a little bit thicker. Okay, and then I'm also going to draw a line from here up to here. This makes it a little bit easier for me to read this off the graph here. Okay, so there's my slope triangle, but to calculate the slope, what we're going to do here to calculate our slope is we go to the rise, and the rise in this case is my tan theta. So this is my change in my tan theta here, and the bottom is my run, which is my change in my current. So if I did my slope calculation, which is going to be my rise, which is my change in my tan thetas, divided by my change in my i's, that's what I would do to get my slope. So I'm going to go down here to this formula. Before I get that slope, I can go up there and calculate this slope in a bit. I'll just pause the video to do that. I'm going to rearrange this. I'm going to go tan theta over I, because that's what my slope calculation is. It's my rise or my run. So I'm going to rearrange this formula above it. So it says tan theta over I, because that is my slope. This is one way to do it. If I did that on the other side, I'll have my ILB mg on the bottom. So all of this stuff on the left-hand side is also equal to my slope. Okay, so I can just drop that middle piece. And I can solve this equation. So I'm just going to rearrange this slightly here to get my b, because that's what we're looking for. Mass times gravity times my slope, all divided by my length of my wire. So I'm just going to find the slope, and I can calculate my magnetic field strength. So I'm just going to pause the video here, and I'll come back with my slope. Okay, so I got my slope here. You can see I drew a bunch of lines here just to kind of measure out what my two values for my rise would be. So I'm going to go y1 minus y2, and then I'm doing the same thing for my x's. Just note that I put a little circle around this times 10 to the negative 2, so that's part of that slope calculation there, so you need that in this calculation. The current doesn't have that, so that's okay. Then I look at my units here. There's no units on the top, but the bottom is in ampere, so this number is like per ampere, so it's kind of a weird units for that one. So I'm going to use that number, so I'm going to go down here, and I'm going to plug that into my equation with the numbers that we have. So we have 2 grams. What I want to do is I want to change the 2 grams into kilograms. Okay, so I would divide that by 1,000. I got the 9.81 meters per second squared for my gravity, or newtons per kilogram, I guess. I like that, actually. I'm going to use the newtons per kilogram for this one. Maybe a newtons per kilogram, okay. Kilogram, like that. And my slope, what I calculated to be 0.05625, per ampere. And then I'm going to divide this all by that 8 times 10 to the negative 2 meters, or the 8 centimeters. Okay, so I'm just going to punch in my calculator quickly. Okay, so I punched it in my calculator. I fixed a little mistake here. So it'd be 2.5 grams rather than 2 grams. And I got a number of 0.0172. And I'm going to assume that these are in Teslas here. You could do some unit analysis to try to figure that out. It's a much weaker magnet than the magnet that we used in our lab. It's just a regular bar magnet, so they're usually pretty weak. The ones in our lab were really close together, and they were neodymium, so much stronger. But that seems like a reasonable number. It's pretty good. So yeah, this is one of the harder graphical analysis kind of questions. This was a diploma exam question from a while ago. Actually, it's a release diploma exam question. They didn't actually use this one. They probably realized how hard it would have been for kids to understand what's actually happening to start off with. But if you see it, you're like, oh, that makes sense. So if I could technically ask a question like this or some kind of graphical analysis question during one of my tests as well. It's fair game. But I'm not going to spring one on here that you've never really seen before, like this tan theta stuff. But it's a fun little question to do. Okay? I'll see you in the next video. Bye.